Hello my schoolers, you welcome to my school YouTube channel. My name is Emmanuel and today we'll be looking at the part 2 of atomic structure and chemical bonding. Please stick around, don't go anywhere, we'll be right back. You're welcome back to my school YouTube channel. Like I said earlier on, today we'll be looking at the part 2 of atomic structure, the chemical bonding also. And then underneath that, we'll be looking at what periodic table is. We'll be looking at the physical trend, okay, of the properties of the periodic table. And we'll be looking at the different types of chemical bonding that exist among compounds. Now, let's get down to it. The first thing we'll be talking about is periodic table. A periodic table, as the name implies, is a table of elements arranged in order of their increasing atomic numbers. Elements that exist. Remember, in the previous video, we talked about the different types of elements we have. All the numbers, whether they are non-metals, whether they are metals, that are in existence. How they were arranged in a table. That is what we mean by periodic table. And the periodic table is a table of elements. Elements are arranged in order of their increasing atomic number. So the basis in which elements are arranged in periodic table, it is on the basis of their atomic numbers, which is also the number of protons that are present in the atom of an element. The periodic table has horizontal rows called periods. Elements in the same period have the same number of shells. And then the periodic table also has vertical columns called groups, ranging from groups 1 to group O. It means that elements are arranged in groups as well as in vertical column, which is what we call groups. And then they are also arranged in periods. So elements in the same group have the same number of electrons in their outermost shells. As a result, they possess the same chemical properties and electronic configurations, while elements in the same period have the same number of shells with similar chemical properties. In other words, what actually determines the basis for grouping elements in their groups and column is based on their properties. They have similarities in the way they behave in their properties. So those of them that are placed in the same group, they have the same number of electrons in their outermost shell, while those that are placed in the same period, they have the same number of shells but different number of electrons in their outermost shell. In such a manner, they are to behave similarly. They have the same chemical properties. Let's move on to the next slide. The modern periodic law states that the properties of elements are the periodic functions of their atomic numbers. That is what it states. The modern periodic law states that the properties of elements are the periodic functions of their atomic numbers. So which means that the periodic function, the way elements are placed in the periodic table, are as a result of their atomic number. So classifications of elements into groups. How are elements classified into groups? We have them ranging from group 1 to group 2, group 3, group 4, group 5, group 6, group 7, and group O. Group O. Some textbooks many years ago we refer to them as group 8, but now group O, because they have completely filled electrons. Their shells, their outermost shells are completely filled. There is no free valence electron. So we look at group 1. Group 1 are referred to as alkali metals. Alkali metals, group 1. Please take note. Alkali metals, not alkaline. Look at the spelling. Alkali metals. Alkali metals, example, we have lithium, we have sodium, we have potassium, we have rubidium, we have cesium, we have francium. Those are the elements you can find in group 1. They are referred to as alkali metals. And then we have the group 2 elements referred to as alkaline earth metal. You can see the difference in the spelling. Alkali metals and alkaline earth metals. They are the group 2 elements because they have 2 electrons in their outermost shell. That's why they are in group 2. We have example beryllium, we have magnesium, we have calcium, we have strontium, we have barium, we have radon. And then we have the group 3 element. They are group 3 element because all the elements in that group, they have 3 electrons in their outermost shell. And then we have group 4 elements, we have group 5 elements, we have group 6, and then we have group 7. Group 7 elements are the halogens. Halogens are referred to as the salt formers. They are elements that form salts. Okay, example, we have fluorine is the first, we have chlorine, we have bromine, we have iodine, and we have astatine. Those are the elements we can find in group 7. They are all referred to as halogens. And group O are the noble gases, okay, or we call them rare gases, or we call them inert gases. Whichever name they call, they are all referred to as group O elements. Rare gases, noble gases, or inert gases. They are inert gases because mostly they don't partake in chemical reaction in most cases, but we have some exceptional cases. Okay, so these groups are just looked at because they have special names. Okay, that's what I want you to take note of. Group 1 elements are alkaline metals, group 2 elements are alkaline earth metals, group 7 elements are halogen, and group O elements are noble gases or rare gases or inert gases. Example, we have helium, we have neon, and then we have argon. Hydrogen is often placed under group 1. Why? Because it has 1 electron in its outermost shell, not because it is a metal. Hydrogen is not a metal. At room temperature, it is a gas. So, but we have to place it in group 1 in the periodic table. By the time you look at it, it is because it also has 1 electron, valence electron in the outermost shell, just like all the elements in group 1. Remember, the elements are placed in group because of the number of electrons they have in their outermost shell. So the reason hydrogen is placed with them in group 1, even though it is not a metal, is because it has 1 electron in the outermost shell. Let's move on to the next slide. This is an example of how a periodic table look like. If you check different textbooks, you check online, you see different categories, different types, different forms in which periodic table could appear. Okay, but let's just look at this. You can see we have periods here. Okay, this is period 1, period 2, period 3. They are always horizontal. Period 4, 5, 6, and 7. And then we have our groups: group 1, group 2, group 3, group 4, and so on up to this group. But if you want to draw the periodic table for the first 20 elements, this group 3 to 12 here is not going to appear there. Okay, so you are just going to draw this one closer, so this gap will not be there. So this becomes group 1, 2, then this will be 3, group 4, group 5, group 6, group 7, and then group O or group 8. So if you are not including this one there, so just take note of the elements we have in period 1, elements we have in period 2, period 3, period 4, period 5, period 6, and period 7. And those ones we have in group 1, you can see them, group 2, group 3, and so on and so forth. So let's move on to the next slide now. Now let's look at the group 1 elements, the alkali metals. These are lithium, sodium, potassium, rubidium, cesium, and francium. The group 1 elements are called the alkali metals. Why? Because they react vigorously with cold water, forming alkali and liberating hydrogen. When they react with cold water, the reaction is so vigorous that they liberate hydrogen. Okay, hydrogen as a gas will be liberated, and then what will be formed eventually will be an alkali. Okay, so their oxides also will dissolve in water to form strong alkalis. Look at example here. This is potassium here. Of course, that is a metal, group 1. That's it. Potassium here reacting with water. You can see that's liquid water to have potassium hydroxide. Okay, this is an alkali, and then to form hydrogen gas. That's gaseous. It is liberated. So we have 2 molecules of potassium hydroxide that is formed. So that is why they are called alkali metals, because when those metals, all of these ones, they react with water, cold water, they will give up hydrogen, and then they will produce what? Alkalis. Okay, that's why we refer to them as alkali metals. They have 1 electron in their outermost shell, and they exhibit valency of +1. Okay, in the outermost shell. That's why you see potassium is written as K+. When you write potassium, you write it as this K+, Okay, you want to represent the ionic state of sodium, you write Na plus. You want to represent for rubidium, you write Rb plus, and so on. The cesium is Cs plus, and then we have francium Fr plus. So all of these ones, because they are in group 1, they have a valency of +1, +1, +1. So because they are very reactive and they can react with air and water, we don't store them anyhow. We store them under paraffin oil, or we just store them under paraffin, okay, or oil, okay. So we don't store them just like any other element, because they are very reactive. When you expose them to air, okay, they can react so fast. And then when you expose them also to water and air, okay, of course, because they are metals, you know what happens when air and water come in contact with the metal? Rusting takes place, corrosion, okay. So they react so much. So we store them under oil or paraffin. They ionize by loss of their one valence electron. Now, every metal will always give up their outermost, the electrons in the outermost shell and become positively charged. Once a metal loses electron, it becomes positively charged. Look at this. Sodium minus, that means it's losing, minus E minus. Of course, this is electron. We said that in our previous video lesson, that this is the symbol for electron, E negative. So when sodium loses one electron, okay, it becomes positively charged, okay. The reverse is the case with non-metal. When non-metals gain electron, they become negatively charged. So sodium loses electron to become positively charged. Sodium and potassium triisocarbonate 4 salts are the only soluble carbonates that do not decompose on eating, but the triisocarbonate of every other alkali members will decompose when you eat them. But for sodium triisocarbonate 4 and potassium triisocarbonate 4, when you apply it to them, they don't decompose. Let's move on to the next slide. We're looking at the group 2 elements now. Group 2 elements are called the alkaline earth metals. Alkaline earth metals. They include beryllium, magnesium, calcium, strontium, and barium. They are called the alkaline earth metals because they have 2 electrons in their outermost shell. They have 2 electrons in their outermost shell, and they are ionized by the loss of the 2 valence electron. Remember what I said about metals? Metals will always lose electrons to what? To become positively charged. Okay, so we have calcium here. This is calcium metal losing 2 electrons to become, because it loses 2 electrons, it becomes 2 plus. If it were 1, like group 1, it would have been +1. But because it is 2 electrons that is lost, we have it there, 2 plus. This shows that what? This metal has lost 2 electrons, and then it becomes positively charged. So they react with steam, not cold water now. Group 1 element react vigorously with cold water. But group 2 element react with steam to liberate hydrogen as follows. We have calcium here reacting with 2 moles of H2O. You can see it gaseous because it means it is steam, okay, to give us calcium hydroxide, and then hydrogen gas is given up. Remember, if it were group 1 element will react with cold water vigorously to liberate hydrogen, alkali metals. But group 2 elements, alkaline earth metals, will react with steam, not cold water now, to liberate hydrogen gas. You can see that in this reaction. Their triisonitrate 5 salts and triisocarbonate 4 salts decompose readily on heating. You can see this is calcium triisocarbonate, okay, solid. You can see that now. It is heated to give us calcium oxide and carbon 4 oxide. You can see this that is given up here. So this is what happens here. Calcium carbonate is decomposed readily on heating. It breaks down into calcium oxide and into carbon 4 oxide. Let's move on to the next slide now. The group 3 elements, they don't have a special name like we have group 1, group 2, group 7, group 8, okay? But let's just run through what the characteristics are. We have examples include boron, aluminium, gallium, and so on. The most common element of this is aluminium. Of course, aluminium is so common, everyone knows about it. It has 3 electrons in its outermost shell and ionizes by the loss of the 3 valence electron. That is why when aluminium, you can see this aluminium metal loses, that's minus 3 electrons. Why is it losing 3 electrons? It has 3 electrons in the outermost shell. Okay, so whenever it wants to bond whenever it wants to combine with another element or other compound, it will have to allow what? It needs 3. So 3 electrons will be what? Will be given up, because it has that in its outermost shell so that it can become comfortable. So it needs to lose those 3 electrons so that it becomes Al3+, because it's losing 3 electrons. Aluminium and its oxide cannot react with water, and so does not form an alkali. So we cannot refer to it as alkali metal, because it does not form an alkali by reacting with water. So aluminium oxide, you can see that Al2O3 and AlOH3, this aluminium hydroxide, exhibit both acidic and basic character. So they are said to be amphoteric in nature. So any compound that exhibits acidic properties as well as basic properties, characteristics, we say they are amphoteric. Another example is zinc oxide. Zinc oxide is amphoteric in nature. It can behave as an acid in a reaction. It can also behave as a base in a reaction. So we say it is amphoteric oxide. So Al2O3 plus H2SO4, you can see that we have Al2SO4 here plus 3H2O. So you can see it here reacting here to have this. So on heating, aluminium triazonitrate 5 decomposes, and then we have this decomposes, it breaks down to aluminium oxide, oxygen, and then nitrate. That's what we call the nitrogen 4 oxide, or nitrogen dioxide. Of course, that's gaseous, and then we have this reaction. Let's move on to the next slide. Group 4 elements, usually we refer to them as bridge elements. Bridge elements in the sense that they are at the middle of the periodic table. Okay, we have the periodic table running from group 1 to group O. So group 1, group 2, and part of group 3 are metallic. Okay, then group 5, 6, 7 are non-metals. Okay, and then we have the group 8 as inert gases. So group 4 tend to stay at the middle, so we call them the bridge elements. They include carbon, silicon. In some periodic table you see them being referred to as a metalloid. Okay, so we have them including, we have the carbon, we have silicon, we have germanium, we have tin, and then we have lead. So those are group 4 elements, and they are tetravalent in nature because each of their atoms has 4 valence electrons. So in the outermost shell they have 4 valence electrons in the outermost shell, and then they have a corresponding decrease in electronegativity, that is the tendency to accept electron. They have it there. Carbon and silicon form more stable positive 4-state compounds, while tin and lead form more stable +2-state compound. That's why when you see carbon, it's written, you have silicon, you can have them as +4, okay, because they have 4 bonds in the outermost shell. But usually tin, in most cases, when you want to write tin, you want to write can exist as +2 and +4, but because they are more stable at +2, so when you write lead, in most cases we write lead this way, 2+, okay, because it is more stable at this point. When you write for tin, you write this, and then you have a 2+, so it is more stable at this point. Now let's move on to the next slide. Group 5 elements. They are non-metals which show 2 common valencies of 3 and 5. 3 and 5 because they have 5 electrons in their outermost shell. So they'll be needing 3 to complete that outermost shell being filled up. So they have 3 and 5 as their valencies. They are non-metals. Example includes nitrogen, phosphorus, and so on. So they are electron acceptors. Every non-metals are electron acceptors, while every metals are electron donor. They give because they have excess. That's why they are positive. Okay, they have excess, so they will always give electrons out, but there's always a receiving end. So it's the non-metals that are always receiving or accepting electrons. So the electron acceptors, as both of them, that's both nitrogen and phosphorus, form several oxides which have parallel characteristics. For instance, nitrogen 3 oxide, that is N2O3, nitrogen 5 oxide, that's N2O5, phosphorus 3 oxide, P4O6, and then phosphorus 5 oxide, P4O10, and so on and so on. All these, okay, are acidic oxides, and they would form acids when reacted with water. They will form acids when reacted with water. Let's move on to the next slide. The group 6 elements. Examples include oxygen and sulfur and so on. We have, when you look at the periodic table, we have them. Just look down group 6, you see them. Okay, but these two we'll be talking about, they are non-metals as usual. As a result, they are electron acceptors. Like I said earlier on, all non-metals are electron acceptors. For instance, magnesium, of course, this is a metal here, reacting with oxygen, which is a non-metal. This is area of concentration now. This is non-metal reacting with metal here. What happens? We have magnesium. Remember, if we were to write this, it will be magnesium metal losing, because it's a metal. Metals we lose. We lose 2 electrons because it is in group 2. We lose 2 electrons to become Mg2 plus. Okay. Then oxygen here, okay, will lose 2 electrons. So we gain 2 electrons because it is accepting. We gain 2 electrons to become oxygen. Then because it is gaining, it becomes negatively charged. So the ones that gain, that accept, is negatively charged. The one that gives becomes positive charge. It's showing you that I have excess. So I give 2 electrons out, so I'm positive, while this is negative. So if you combine the two together, that's why we have Mg2 plus O2 minus. It means that the 2 electrons that this magnesium is giving out, this oxygen is accepting the 2 electrons. That's how we write it this way. So while oxygen is slightly soluble in water, sulfur is completely insoluble. So both oxygen and sulfur combine directly with hydrogen to produce water and hydrogen sulfide respectively. So what we are saying is that oxygen and sulfur will combine directly with hydrogen. If oxygen combines with hydrogen, of course, you know we are going to form water, that's H2O. And then when sulfur reacts with hydrogen, we have hydrogen sulfide. So that's the reaction that takes place. Now let's move on to the next slide. Group 7 elements. We talked about this, that they are called halogens. Group 7 elements are called halogens. They are called halogens because they are salt formers. In other words, when group 7 elements or non-metal react with metals, we will always have salts that is formed. Salts will be formed whenever a non-metal, especially the group 7 elements, react with metal. We form salts. Salts are formed. Okay, so that's why we call them salt formers. They are fluorine, we have chlorine, we have bromine, we have iodine, and then we have one other one, astatine. Astatine, we don't mention it most times with them because it is always in free state. At room temperature, it does not really. So it is why the reason we refer to fluorine, chlorine, bromine, and iodine. We talk more about these ones as the halogen, but don't forget also that astatine is also one of them. It belongs to that group. And then they are non-metals. Like I said earlier on, they have 7 electrons in their outermost shell and ionize by gain of 1 electron. Ionize by gain of. When we talk about having 7 electrons in the outermost shell, see what we mean. We have, let's take the first 2. Fluorine, for instance. Fluorine is F and it has atomic number of 9. Chlorine is Cl, it has atomic number of 17. So if you write the configuration of this, remember according to Hund's rule, Pauli's exclusion principle, and the other one we talked about in the last class, we said the first shell can take 2, then take 2 from 9, we have 7 left. So and the second shell can take 8. So this is not up to 8 here. So that's 7. And then this one, the first shell will take 2, second shell can take 8. Okay. Third shell also 2 plus 7, 8 is 10. 10 from 17, we have 7 left. So we have 7. So you can see 7 electrons in the outermost shell. If you roll for bromine also, you will see that we have 7 outside. Iodine, we also have 7. So they have 7 electrons. If you draw that, okay, for fluorine, 2 will be here. The second shell will take 7. If you are drawing for chlorine, the first shell will take 2. The second shell will take 8. And then the third shell will be 7. So you see the outermost shell, the last shell, that's what we call the outermost shell. It has 7 electrons. So that's why they are in group 7 elements. So we say they ionize by gain of 1 electron. The reason being that there's 7 electrons here, and we said that for this to be completely filled, it must be 8, and we have 7 here. So it needs just what? 1. So that's why we say it is -1. The same thing happens here, it needs 1. So 1 electron. So that's why it will ionize by what? By gaining or accepting 1 electron, so that this will be completely filled. That's why we have Cl plus E minus plus 1 electron, we have Cl minus. So remember, the substance that accepts electron becomes negatively charged. The one that gives electron becomes positively charged. And those that give electrons, most cases, are metals. Metals donate electrons. They give electrons because they have excess, and then they become also satisfied. So halogens exist as diatomic molecules. For example, we have fluorine as F2, chlorine Cl2, bromine Br2, iodine I2. You can see them 2, 2, 2. That's why they are diatomic, okay, as molecules. That's how they exist. So they are very reactive non-metals. In fact, they are the most reactive non-metals. If you are asked what is the name of the element, the most reactive non-metals, okay, the strongest, it is what? Fluorine, because fluorine is the first on the periodic table. So as you go down the group, it begins to what? To decrease. You will see that the trend, by the time we look at the trend in the properties. So we see that happening here. So you can say that they are very reactive non-metals. Halogens have similar chemical and physical properties. They are hydrides, which are gases at room temperature, dissolve in water to form acid. You can see them. Hydrogen reacts with this to form HCl. HCl now reacts with water on further to have what? HCl. Now, look at these two things. They have the same formula, but their names are not the same. HCl, when you see the state as gaseous, it is referred to as hydrogen chloride gas. But if it is HCl as aqueous, it becomes hydrochloric acid. The same formula, but different name. Let's move on to the next slide. Group O elements. These are the inert gases. They are noble gases or they are rare gases. Whichever one you call them, you can refer to them as inert gases, as noble or rare gases. They are helium, argon, neon, krypton, xenon, and radon. They are inert or highly unreactive. Why? Because they have their outermost shell completely filled with electrons. So they are the most satisfied group of electrons. They don't need any electron, neither are they giving out. They don't receive, they don't give. That's why in most cases they are inert. They don't undergo chemical reaction. But we have some exceptions, they still go, but in most cases, okay, you don't have them. So that's why they are inert. They are unreactive. The word inert means unreactive. Their unreactive nature can readily be understood from their electronic configurations, which satisfies the duplet in the case of helium, and the octet rule for stability. Also, consequent to their unreactivity, they form few compounds and exist freely. When we say freely, in their uncombined state as monoatomic molecules in the atmosphere. Now we've come to the end of the preview of this video lesson. If you want to have access to the full video, please click on the link in the description below that takes you to my school website where you have access to subscribe. And in the full video, we'll be talking about transition metals, we'll be talking about lanthanides and the actinides, we'll be talking about the different chemical bonding that we have. I hope you enjoyed this video. If yes, please don't forget to click the like button, hit the subscribe button, and finally tap the notification bell to keep you notified once we upload our next video.